I am Dr. K.C. Jain, and it is the fourth lecture for the elements of electrodynamics. In this lecture, we will discuss about the Maxwell's equation, the derivation of Maxwell's equation, as well as the solution of Maxwell's equation. As we already know that Maxwell's equations are very important, and these equations are the basis of the theory of light, which is given by Maxwell's. These equations are from the equations of electromagnetism. So two equations are from electrostatics and two equations from electromagnetism. These equations already we have derived and we have understood in our previous lectures. Now one by one we will divide these equations. So first equation, divergence D is equals to 0. So according to Gauss's law, we can write E dot ds is q upon epsilon naught, that is closed surface, the q, and q we can write rho dv. So it is E dot ds, that is equal to 1 upon epsilon naught rho dv. From the Gauss's divergence theorem, we can convert the surface integral into volume integral. So E dot ds we can write del dot E divergence dv. So del dot E dv is equal to 1 upon epsilon naught rho dv, and del dot E is rho upon epsilon naught, or del dot D is equal to rho. That is the first equation. Now the second equation. As we know that incoming flux is equals to outgoing flux in a closed surface, or we can say net magnetic flux is 0. So we can write for a closed surface we can integrate B dot ds, and that is equal to 0. From Gauss's divergence theorem, we can convert again surface integral into volume integral, and we can write B dot ds is del dot B dv equal to 0. That is del dot B, divergence B is equals to 0. Now the third equation. Del cross E is equal to minus del B upon del T. We have that induced EMF E is equals to rate of change of flux, that is E equal to minus d phi by dt, and we can write this equal to minus d upon dt. As you know, phi is equal to B dot ds, so we can write minus d upon dt B dot ds, and also induced EMF also E, that is equal to minus E dot dl. So E dot dl is, we can write minus d upon dt B dot ds. So E dot dl we can write, if we take the differential operator inside integral, so we can write minus dB upon dt ds. According to Stokes theorem, line integral converted into surface integral. So E dot dl is, we can write del cross E, that is curl of E ds, and so it is equal to minus dB upon dt ds. So del cross E is minus dB del B upon del T. That is third equation of Maxwell's. Now the fourth equation, that is del cross B is equal to minus mu 0 J plus del D upon del T. So we will use here the Ampere's law. So according to Ampere's law, B dot dl is equal to mu 0 I, and that we can write mu 0 integral J dot ds, where J is current density. According to Stokes theorem, line integral can be converted into surface integral. So B dot dl is equals to del cross B ds. So del cross B ds is equal to mu 0 J dot ds. We can substitute this B dot dl, we can write del cross B ds, so del cross B ds and mu 0 J dot ds. Now del cross B is equal to mu 0 J for steady currents only. This is only for steady currents. Now for time varying fields. Time varying fields, del dot J equal to minus del rho upon del T, taking divergence both sides. So del dot del cross B is mu 0, del dot J we can write. So del cross B is equal to 0. So del dot J equal to 0. It is not according to equation of continuity. Hence it is modified by Maxwell's by using concept of displacement current, as earlier we have discussed in lecture 2. Del cross B is equal to minus mu 0 J plus JD. That JD additionally displacement current that we have used in previous lectures. Now we are again, additional term is taken as JD. So del dot del cross B, again taking the divergence. So del dot del cross B is equal to mu 0 del dot J plus JD. So it is 0, and mu 0 del J plus del dot ZD. So del dot J is equal to minus del dot ZD from this equation, and it is equal to minus del rho upon del T. But del dot D is equal to rho from the first equation of Maxwell's. So del dot ZD is equal to del upon del T, del dot D. So del dot ZD is basically del dot del D upon del T, or the value of ZD we can write del D upon del T. So del cross B now is mu 0 J plus del D upon del T, or del cross B is equal to mu 0 J plus mu 0 epsilon del E upon del T. This is the fourth equation of Maxwell's. Now, for free space, we can write del dot D is equal to 0, del dot B is equal to 0, del cross E is equal to minus del B upon del T, and del cross B is equal to mu 0 epsilon 0 del E upon del T. Free space means there is no charge there. So in all these equations we have this current density is 0, and in first equation that we have written del dot D is equal to rho. So rho again is 0 because it is the charge density. Now we can solve the Schrodinger equation for free space. So this is equation number 1, it is equation 2, this is equation 3, and this one is equation 4. So these equations we can say equation 1 again for free space, equation 2, equation 3, and equation 4. So we can solve these equations for free space. So taking curl of equation 3, this equation we can have the curl. So del cross E is equal to minus del cross del B upon del T. We can write this as del dot E minus del dot del E, or del square E is equals to minus del upon del T del cross B. So del cross E is equal to minus mu 0 epsilon 0 del square E upon del T square. This term is 0, and this term we can write del square E. So del square E is this. Similarly, if we take the curl of fourth equation, this equation, then by using the same technique del square B, we can write mu 0 epsilon 0 del square B upon del T square. Now on comparison with wave equation, del square psi upon del square psi is equal to 1 upon u square del square psi upon del T square. This is standard three-dimensional wave equation with wave velocity u and time t. This equation we have already used in the chapter of wave mechanics, where we have derived this Schrodinger equation from this equation. So if we compare, then this u comes out to be 1 upon under root mu e, because here this is mu naught epsilon naught, so mu naught epsilon naught. So this, if we compare this, then c is equal to 1 upon under this. If we compare, then u comes out to be 1 upon under root mu naught epsilon naught, and if we substitute the value of mu naught and epsilon naught for vacuum, then u it comes out to be c, that is 3 into 10 to the power 8 meter per second. For medium, u is equal to 1 upon mu naught epsilon naught, and epsilon is epsilon naught epsilon r, and mu naught is mu naught mu r, and we can write, then this comes out to be this u is equal to 1 upon under root mu naught mu r epsilon naught epsilon r, and we can write u is equal to 1 upon this mu naught epsilon naught is 1 upon under root mu naught epsilon naught is c, so we can write c, and in under root it will be mu r epsilon r, and this u is equal to c upon under root mu r epsilon r. Now the u upon c is 1 upon under root mu r epsilon r, and this u upon c is refractive index, the velocity of light in medium divided by velocity of light in vacuum, and that is 1 upon under root mu r epsilon r. So this, if we substitute for these values for glass, then it comes out to be 1.5. and that is the refractive index of glass. So what we can say from here, that the Maxwell's equations that we have derived are moving with the speed of light and have the properties of light. So we can say that Maxwell's equation truly represents the light.